Hey, John here. I'm getting ready to do a couple of experiments with the TI-99 VDP to discover what's going on in the status register over the course of time if you pull it continuously while it's painting a frame. A big thanks to all the VIPs shown here for supporting my channel above and beyond Call of Duty. Thank you very much. And also a big thanks to all the likers and subscribers and Patreons out there that give me a hand with all this stuff. Thank you very much. Now let's start with a discussion of why the heck I'm even talking about this right now. I ran into this thread on a chat in here. What am I looking at? I don't know. Atari Age, blah, blah, blah. VDP's fifth sprite on the line. So I was looking at some stuff. I heard of some people using a technique for some game development. And this particular post, I think, outlines the specifics very clearly and in the most succinct fashion. Now, this is running on an MSX, and they say MSX. I'm pretty sure they meant an MSX2 because some of the stuff in here, they're showing 8 sprites per line when we all know that the VDP 99 chip from TI, that can only show 4 per line. So this is the more enhanced VDP, but it doesn't matter for the sake of our discussion. And this thread, as you just saw, it was titled 5 per line or 5th sprite per line. And so the point is they both work the same way. It's just that the MSX had a VDP that allowed you to have 8. So this person here goes on to describe a technique that they use to flip this sprite attribute table address and the sprite pattern table while the screen is being rendered. And what they're going to do is they're going to use one set of sprites up here and then change to a whole nother 32 down here, giving them 64 at most on the screen at any one time, with, in this case, 8 per line. In our case, it would be 4 per line. But the same technique holds true. So what they do is they say, look, when the game plays, the score bar is made up of 28 plus 1 sprites. The first 24 are 8 per line. The last 4 are the white sign. The 29th is hidden and is used to trigger the screen split. So if we scroll through this game, what you can see here, I don't know what the white sign is. I guess I got to play it to get this junk off the screen. Maybe just get the mouse. I guess it wants to overlay. Thank you, YouTube. In any event, the score bar, these guys up here are going to be the 8 sprites that they're talking about. Probably 2 digits per sprite. Is that what's going on here? 1, 2, 3, 4, 5, 6, yeah, 7, 8. I guess it's 1 sprite per digit. And maybe more up here for this thing. I don't know why they would use sprites for that and not regular tile patterns. I don't know. But nonetheless, that's what they're doing. And what they've got here is they put on purpose a lower priority sprite off to the right over here, causing the, in this case, it would be the 9th sprite on this VDP. In our case, you could use the same technique and put a 5th one over here that can't be rendered, or that is invisible and stuff like that and wouldn't be rendered anyway, or off in the right border, wherever you want to put it. As long as it's a higher numbered sprite, lower priority, you would see the 5th sprite be reported in the VDP status register. As you recall, it looks like this. Now remember that you need to think about this just right here. The status register doesn't report status about the last frame it rendered. It reports the status of what has taken place since the last time you read the status register, which may or may not have happened in the last frame. You let your system idle for more than a 60th of a second. Multiple frames will have been rendered before you will go back perhaps and read the status register again, all right? So be careful how you phrase this or how you understand the phrasing of the discussion we're going to look at in here. It absolutely will report the first time that it sees a fifth sprite on a line since the last time you read the status register. Same is true about collisions, but that's not so important because any collision is going to get reported anyway. It doesn't change. It's more important to where this is concerned because you could have many rows on the screen that have 5 sprites in them, and then you have to ask yourself the question, well, which fifth sprite do you see in the status register? And it turns out, as I've said, it is the first one encountered since the last time this was reset, and it gets reset every time you read it. The same holds true about the frame flag, okay? Now, they're going to continuously pull that status register looking for a fifth sprite to be flagged. And it turns out that the real TI, chips update that fifth sprite number and the fifth flag, and it makes sense, when it happens, when it encounters it while it's rendering the screen from top to bottom. It would require actually more circuitry to hold off and report it later. You need more latches and stuff. So it turns out it makes a fair amount of sense from the implementation, simplification of the implementation of the chip itself. So what they've done is they put a fifth sprite up here, maybe, I don't know, down here or something. Maybe this is the white sign they're talking about. I don't know. When it hits this fifth sprite, what they want to do is change the sprite attribute table pointer to start using a different sprite attribute table and a pattern table so they can draw these ships. If we hit play here, you can see an awful lot going on. Now, you've got some pretty fancy colors in here. There's a lot of colors going on in here that you can't really do with the TI-99 style VDP. I don't think we can do this either. That's 3 colors in one area. Well, you can by stacking sprites on top of each other, but you would run out of sprites even in this setup. I suspect that the MSX2 has, in fact, the short blurb on the enhanced VDP in the MSX2 does allow more colors in their sprites and stuff like that. So this would be hard, if not impossible, to do on the regular VDP. It also provides higher screen resolution, which would also be necessary to render a ship like this. So some of this is fancy because of they have higher resolution graphics, and other aspects of this is they need more sprites than they can fit on the screen, which is the whole point of why we're talking about this today. So there's a little more fanciness going on up there because it's a fancier machine, but the technique still holds true is the whole point here, right? So what they do is they purposely put too many sprites on a line up here in the top part of the screen so that the fifth sprite flag goes on while it's being rendered. And if they pull the status register all the time, they'll see that flag go on when it's still rendering up here. They then update those table pointers, and as it renders the bottom half of the screen, we've got a whole bunch more sprites than you could otherwise have on the screen at the same time. So they actually give you the actual code that they use here, and this would basically work with the regular TI VDP as well. What are they going to do? This is actually an interrupt handler. And I would not put this in an interrupt handler. But if the machine is, a single tasking machine with a dedicated purpose, sure, why not? You can go ahead and do this. And what I'm talking about is this spin loop right here in an interrupt handler. That's not a nice thing to do on a machine with multitasking, okay, or any fancy sort of thing going on. But the technique still holds, and it would work. So what do they got? An interrupt goes off, presumably because they've got the end of the frame. They save everything. They set up the attribute in the pattern table, the sprite attribute in pattern tables for the top half of the screen. And then they go into a spin loop, and I wouldn't do this either. I would also put a counter in here, so I would give up after a while. Otherwise, you're in an interrupt handler spinning. If this never happens, you've just seized the machine. Again, there's some techniques in here you may want to think about before you do them in a regular program. But in any event, as long as everything works perfectly and there are no glitches or race conditions, which we already know also exists in the regular TI 9918 or the 9118, those VDPs, where we can miss a flag being set. Certainly the frame flag bit can be missed in a certain glitchy race condition between the CPU bus and the internal TI-99. We talked about that in another video. In any event, assuming that all works fine, and maybe it does on the MSX, the more enhanced VDP that they've got, maybe they did a better job synchronizing the registers in there. The point is they read their status register, I guess from that address there. They shut off the flags they don't care about, or the bits they don't care about, and then they want to say, look, I want to know, what is he doing here? He's going with a 5F. So in binary, that means 0101111. So he's looking at this and this over here, and he says, if that exactly equals 5C, and they say plane 28, which is the sprite number that they hope to see appearing as the fifth sprite in a line. When that happens, we fall down, flip the tables, and leave the interrupt handler down here. Otherwise, we keep waiting. So this is the technique, right? And I'm interested in this because when I wrote my VDP code for the Nouveau, I did not update the fifth sprite status bits as the screen progressed, okay? So I made a one-line change to my implementation that then did this. As soon as I saw the fifth sprite, I stuck it in here so that if someone wrote code that works like this on the Nouveau VDP, that it would still work and they would see it go live, the flag would go on and the sprite number would go in there, and it would be locked into the register while the thing is being painted, so that this technique would work, so we can use it and make games with more sprites as well. So, okay, so that's what's going on here. And the rest of what we want to talk about is to have a look at what really is going on. Now, I'm logged on to my retro board here, and I've got a screen capture over here showing you what's coming out of the VDP. Now, let's go over to drive C. I've got some test programs on here. I think we've seen this one before. We've got a couple of variations of this. App that was written by Production Dave and shared with us on the Discord. Now, these glitches in here are caused by this particular version of the code. He's polling the VDP while it goes, and he's also reading the status register in his interrupt handler. So this is an artifact of this version of the code. So I'm not that concerned about this glitchy behavior on the screen. What we want to look at is what the CPU is doing when it's polling the status register, and these glitches are just part of, like I said, this particular app. Now, to that end, what I'm going to do is I'm going to stop this program. I think I hit Q or escape or something, and it stops running the program that updates the screen. Because it doesn't reset the VDP or anything, when the program ends, the VDP is still rendering whatever is in the VRAM, and perfectly stable. Not much changing anything. No one's polling or anything like that right now. So this is what the VDP is rendering at this moment. Now, I hooked up my scope like this. I got 3 probes. I only have a dual trace scope, but I'm using the external trigger on this gray probe here. The gray probe is on this diode right there, which is the raw interrupt pin coming out of the VDP. This probe here, which is the purple trace, is on the I/O request line coming right off the CPU. and this one is clipped to the video, the composite video signal coming out of the retro VDP board. Now, if we run a program, let's go over here and do this. Now, I'm going to use ZSID instead of DDT because I have some programs that I wrote that use Z80 opcodes. One of them is called rdf.com. If we look at this program, very simple. It reads the status port and throws away the results. And like I said before, remember the status register can get updated while it's going, and it will stay set to whatever was last there since the previous time you read it. So I'm going to read it once and throw it away to reset the status register. That's the point of that instruction. This one now is going to be part of this loop here, this 3-instruction loop that says read it in, wait for the frame bit to go on. If the frame flag is not set, go back here and spin. Now, this is me waiting for that end of frame bit to go on. When that's done, I simply return from the app. So if we just run this program, we're doing RDF. And if I can get my scope to trigger right, we end up with a screenshot that looks like this. So here's the, the composite video comes in a yellow trace, the IO request pin is here, and the sync is here, and you can see this marker there saying this is where the scope has become triggered from the interrupt request signal going from high to low. All right, so that's how to read this scope. And you can see that the polling, looking at the, the IO request line from the CPU stops right here. So that gives us a pretty good clue that I've never shown in any of the videos on my channel before, which is why I want to do this now, that when the interrupt signal that leaves the VDP is asserted, that the status bit in the VDP status register for the frame flag goes on at the exact same time, or certainly close enough. If we zoom way in on that, what do we got here? You can see what is, we'll take a closer look at this in a minute, but this is the bottom border, the first scan line of the bottom border, and you see the polling stopping here when the interrupt's supposed to go off. I can zoom in a little bit closer, and we can get a really good close-up of what's happening here between the time the interrupt goes on, and you see I'm polling. The interrupt hasn't been asserted here, so it goes around in a loop. The interrupt goes on. The first time I poll it after that happens, I see, hey, the interrupt is asserted, and I stop and I return from the app, okay? So this, to me, I've run this to let me know that the status register does not report the interrupt that has been asserted too early or too late. This is actually letting me see what's actually on that interrupt line right now out of that VDP status register. And that may not be the case. So this confirms that that is, in fact, true. And if you look at this, I've run it. I just recaptured a few other tests, and you can see, based on the randomness of the clock of the CPU, even if I pull it like right after the trigger and the interrupt would have gone true right at this point, I can see that it's on. So modulo whatever, clock jitter and delay and synchronization issues may occur, it gives me a live view of what's going on. Okay, big picture here, no pun intended. This is the image of this screen right here. So let's make sure we all agree on what we're looking at here. I submit this is the bottom border. It's yellow. You can see the chroma signal up there. This has very little chroma. There's a little bit here, a little bit there. And the rest of it looks like it's white or gray. So that, I argue, is this very bottom line on the screen right here. And we know that is the case because if you look closely, what you have here is a thin, maybe 1 pixel wide black, followed by a whole bunch of white stuff with a little bit of noise on the scope, followed by another black that looks like maybe it's wider, maybe 2 pixels or 3 pixels wide. and then white before you get to the right border, which has a higher chroma subcarrier amplitude for the yellow. Okay, so if you zoom way in, let me see if I can do that over here with this viewer. Yeah, there you go. The very bottom line is all white except for the descender on this P and the G. You can see the G is about twice as wide as the P. That's that white line right down here. So that's what's really happening, and we can see that on the scope here. And the reason I submit this as important is because we want to know what the video signal is doing while we're polling, and the only thing we can use as a time reference is the interrupt output and these polling signals that we could see with the scope if we want to look at that, that particular signal. All right, so we know that the VDP asserts the interrupt at the end of the first line of the bottom border. Now, why it doesn't do it over here, I don't have any idea. My implementation in the Nouveau does assert it over here. In fact, mine asserts it way over here during the right border after the last active region scan line. So I'm a little earlier, and I would argue you want it as early as possible to give the CPU as much time as it can possibly have during this period when the VDP is not, rendering all these pixels and interacting with the video RAM, because that's the time, the only time you have before it starts rendering again to update, pattern tables and things like that. So you want as much time as possible. They've wasted, in my opinion, an entire scan line because they've waited until over here. Be that as it may, what we do know is that the interrupt is in sync with the status register F bit over here. So if we want to, we can calculate everything that we're doing in software based on this point in time here. So for example, if we know how fast we poll the status register, we can calculate how many polls we do per scan line that's being rendered. And then we can get a general assessment of what we're looking at in the status register. For example, if there was a fifth sprite on this very bottom scan line, we would know where to look if we poll and save all the data that we see, all those read bytes from the status register. Now, to that end, let's look at another one of these little test programs I brought together, just inir.com. Let's go azsid. It's not com. 100 to about 150. I just type these opcodes directly in zsid, by the way. You don't want to see me type 32 of these in along with a bunch of no ops and a return down here. But that's all this thing really is doing. A whole bunch of INIRs. Quick recap of what this instruction does is it says I'm going to read in through one I/O port. It's going to do an input operation by reading from the port in the C register, which because of this instruction is 81, and that's our status register address for our VDP. And it's going to read in from that port as many times as there is in the BC register. And if you set the BC register to 0, it'll do 256. Every time it does an input operation, it will decrement the B register. And if it is not 0, it will literally set the program counter back up and refetch this instruction and execute it again. Until after the decrement BC, or the B register, I should say, becomes a 0. And then when that happens, it falls down to do the next instruction. So by doing this like this, what happens is the B will go from 0 to FF, FE, and go all the way back down to 0 again. And the next instruction will be started, at which point in time BC will still be or return to the value of 0081. So it'll do another 256, 256, 256, and so on. All right? Now, what's HL used for? Well, HL is the register that holds the address where the input bytes will be stored each time the input operation is done. So when this does an input and decrements the BC register, it also increments the HL. So what we're really doing is polling that status register as fast as we can and storing every one of the polled values into memory starting at 1000. And we're doing that 256, 512, and so on. 32 times 256, which is 8K bytes worth of polling. And then this program will end. And when this program ends, the data that was read and stored in memory will remain in the RAM. Okay? So if I ran this from the command line, what would happen is it would load up program, it would execute the program, return back to CPM. And starting in memory, while I'm back at the, the disk prompt here, oops, this darn terminal, let me get out of here. Hello, there we go, dir. If I ran this, it would from here, and I can go ahead and do that, it will run its entirety, and it would leave all that data in the memory. And in CPM, I can type save, and then I can give it a number, which will save all the pages, where each page is 256 bytes, into a file. So if I wanted to capture all the data that's sitting there in the RAM, I could say, what do I need? I need, if I did 32 pages, that would be fine, because that's how many pages worth of INIRs there are. However, I have to add more, because it starts at 1000 in hex, but it starts saving from 100. So if I go to 64, that's more than what I want, which covers what I really need, and I can then save it in a file. Let's say I call it X. Now, if I look at the A drive, it comes with a program called dump, and I wish it was a nicer program. Maybe someday we'll write a better one. A:dump. And I can dump out this X file, and we can watch it come up on the screen. And when this gets down here, see all these 5s? This is the status value, and there's the extra data. Now, this is a little bit inconvenient to do in this way, but my point is, if we wanted to save a copy of the data, this is one way that you can do that. Now, if I do inir.com, and they say L100 to 150, this is where we were. If I just run it from here and then put a breakpoint and stop it down here, which is why I put these extra no-ops in there, I can never remember if it stops before or after. If I put it on 149, I think it stops before, but it's much easier, and absolutely no doubt if I put a no-op in there and I say go to 100 and stop at 147, that is where I will be. I can then say D1000 in here up to 2FFF, which is exactly the amount of data from the starting point that I want to look at. 8K is 2000 in hex, as I like to say. And you can see all this data go by in here. Now you see all these 05s, and sometimes there's an 01, there's an 03, and so on in here. Now what you can find out is that this is what's happening in the status register. If you just, like I said, if you just pull the heck out of it, this is what we're looking at. Okay? Now this particular test program has sprites number 0 through 4, a total of 5, and then sprite number 5, which is the 6th one, is set to D0 in the X position, which tells the VDP to stop scanning the SAT. Okay? Now, when it stops scanning the SAT, it'll do so, while 5 is the sprite number that it last looked at. So what we're looking at in here is a real-time view of it scanning this sprite attribute table once for each line. Now, as I explained before, the very first time you read, there'll be garbage in there. And what we see here is an 05 with that most significant bit set, because the interrupt flag, or the frame flag, I should say, was still set from the last time this status register was read. And we're not running, we're not doing anything right now, so it's, updating that status register at 60 hertz while I'm yammering on, and no one's reading it. So if I run it again, there'll always be the interrupt flag, the frame flag will always be true on that first read. So let's discard this one in our minds, all right? Now, because we only read 6 of the sprite entries, or actually 5, there's not a lot of reading that's going on. This program is useful to see the 5th sprite disappear, and we can watch what happens if we look at the status after the frame flag has been set. But this program is not optimal for showing us what we see, because it takes about 8,000 polls to see the entire screen in terms of, the total time it takes to render the screen versus the rate at which the INIR instruction runs on the Z80 Retro. Now, in that regard, how did I figure that out, right? Well, you look up the instruction timings, and you find out it takes 21 Z80, T states for each time the INIR instruction goes around one time. And then it takes 16 cycles the last time when it falls through the next instruction. And we know our clock is running at 10 megahertz, so you can do all the timing and figure it all out. We also know, if I zoom in on one single line, this is looks like the bottom border, that it takes 63.5 microseconds per scan line, okay? So substituting all the stuff we know that a 10 megahertz CPU is, 0.1 microseconds out of a total of 63 for this whole line. And if each one of the INR iterations takes 21 clocks, we find out it takes about 30.23 INIR instruction iterations per scan line. So it's on average, it's about 30 and a quarter. And once in a while, it'll take a little bit less time. So this is not perfect calculation. You do the math, you come out with 7,904.7 total INIR samples, give or take, for the whole screen, which is why I set 8K as my target for the total number of samples that we're looking at here. So this should include a full screen rendering and then wrap around and start again, okay? Now, as I said, this is not the most optimal test program, and I only say that because I've written another one. In this particular case, this program will provide a better view of what's going on, because this program plots all 32 sprites on the screen. Now, I can move this cursor around, I think, with the keys. I don't remember which keys move it. There we go. I'm moving it up. I move this up because I know this is like sprite number 0, sprite number 1, this is sprite 2 and 3, and then 4, 5, 6, 7, all these other ones. All right? Now let's zoom in a little bit on this. Zoom in there. Now the goal here is to get a closer look at the status when there's a lot going on. Now, if you look closely in this section of the screen, when you move this thing around, you'll see some pixels disappearing, because these become the 5th sprites. This is sprite number 0. So if I move this up to the top, you see all these little bits disappearing over there. Let's move it to the left some. View there. Okay, so what is happening is we've got a 5th sprite here. When you come up here, you'll notice they're not disappearing. This one's kind of hard to see because it's black on black. And then you got what is that, like a a bright green and a paler green and a purple and so on. So what we've got is these two sprites. This is a third, there's a fourth. This one down here, this lighter green, if I move this down stump and it's in line with this black one, this one, and that one all at the same time on this line right here, that paler green guy will disappear because he becomes the fifth sprite. And you just see that happen. That's right there, okay? So let's leave this right here. And we know that that sprite, I believe that's sprite number 7. That's partially obscured, or it is the fifth sprite. And it's, I don't know, each one of these is 8 rows high, so that's going to be like 16-ish, give or take some. And then we've got our fifth sprite flag on, if this is doing what we assume it does. So with that on the screen, again, I can quit out of this. I think I hit Q, or, yeah, there you go, to stop it. And then if I run my INIR again, if I spell this right, ZSID, that stands for Z80 Symbolic Debugger, I believe, by the way. And that's a CPM app that I put on the standard A drive image. And I can't type and talk at the same time. A:/ZSID-INIR.com. L100 to 150. I forget how far I want to go. I want to stop there. Well, if we run this one, the only thing we've done is we've drawn a different image on the screen that has all pixels, or all the sprites in use, rather than only 5 or 6 of them, okay? So let's say go to 100, stop when we get to here. Now we can say 1,000 to FFF. Now you see this kind of barber pulling effect. That's because when we did our math, we figured out the total number of samples, how many of them happen per line, and so on. It turns out we will get 30 samples at the INIR speed at 10 megahertz per scan line, and once in a while, it'll take 31, because it'll comes out to 30 and a quarter, okay? So look what we got here. This one really stands out because we scan all 32 sprites. Every time we see a 1F, it's easier to see than an 05 versus an 00 and so on. When we're sitting here at 1F, I believe we're in the vertical retrace, vertical blanking period. See that 9F right there? That is 1F with the most significant bit turned on. That is the sample where we see the frame bit on in the status register. So if you backtrack from here, 30 samples, 30, 30, 30, 31, every now and then, you should see one scan line load worth of status reads. So this one here, that would be 16, that would be 32, 31, 30, all being highlighted right there. I would believe that's the samples that take place. Well, I think what we're looking at is the sprites. It's not scanning them because it doesn't need to during that bottom border. That's what we're seeing, that number 31 over and over again during this period here. If we go back another 30 or 31 samples, we'll see what it was doing when it rendered this line right here. So from here, there's 16, there's 32, 31, and 30. So this is a great sample, and it doesn't always come out so nice because we're not scanning it, we're not polling it as fast as it's scanning its sprite table. And you can tell in here, look what it's doing. While it's rendering that bottom line, we see a 0, 5, 7, 0, A, C, D, E, F, 10, 11, 12, what it's doing is it's counting up. Now, I would argue in my implementation, what I put in that fifth sprite number field is the sprite number that I am using when I'm scanning the SAT table. Now, they can't possibly be doing that because if you think about it, if there are any sprites on that last line, look at how often it's counting. It counts more than half of the time. That it's almost the whole line as it counts up in that sprite number. And sometimes it's a 0. That could just be, again, one of these glitchy read setup and hold time things. I mean, the chip is not specified to tell us what we expect to see in that field when the 5th sprite flag is not being set, and in no cases is it set, by the way, in this scenario. But we can see it counting as if it's kind of asking, are you the 5th one? Are you the 5th one? That kind of thing. Maybe it's trying to figure it out as it goes. Now, I bring this up because when I wrote my implementation, what I'm doing is, now I don't generate composite video. During the right border of a scan line, what I do is I scan the attribute table during that, starting at the end of a line for the following line. So if we look closely, if you watch my video on how my sprites work, I scan it over here on the left. At that point, during that time, I decide whether there's a 5th sprite or not, and if there is, I put it in the 5th sprite field, and I set that flag. And if it's set, it stays set until you reset the status register by reading it. Now, I don't know how the TI-99 does it, because in terms of the timing and the interrupt and the sampling that we're just looking at, and here it is, we know that these reads are taking place across this entire line. So therefore, it can't possibly be scanning the attribute table during that time, because if it had to render any sprites on that line, it would be too late to do so, all right? And again, we know that up on top when we actually have sprites. In this particular sample, or this particular example, we do have, it turns out there's the sprite on the bottom scan line right there. There is one down there. It's not a 5th, there's only that one there, and it is on the far right side. It's like number 3 or something like that. So I don't know what or how it does this, but the facts are, this is what we see. Okay, now this is logically the bottom of the screen. If you scroll down here, all the 1F, if you count all this out in 30, 30, 30, 1, 30, 30, 31, and so on from this here all the way down to there, it should come out, within a sample or two to find that this is the scanning during the first line being rendered on the screen. So if we scroll down a little bit, we see some junk over here visually in the ASCII part of the data. See all these 07s? This is when it gets to the point where we've got sprite number 7 over there. Remember what I told you? This is 0, 1, 2 is down there, 3, 4, 5, 6, and 7 is disappearing now as it's the 5th sprite. So what we see is when this green starts rendering the rows that have that 5th sprite for number 7, it shouldn't be scanning the entire 32 entries anymore. It could, but there's no reason for it to do so, because once it gets to the 5th one, it can stop. This 47, in fact, right there is the 5th sprite flag being set with a 7 in it right there. That is the one true time where the manual says that's what you're going to see. There's a 7 in here, and there's a 1 over here. We should also probably have collisions because they're all stacked up on top of each other. And yet we don't. That's very interesting. I would expect it to be a 67. Well, that's a discussion for another video. You see some 27s. Oh, of course. Yes, okay. Yeah, another interesting insight into the TI implementation here. The collision bit is set when we're pulling over here. And again, we reset the status register every time we look at it. And when it's rendering this picture, it is colliding over here. And we see it while we're polling. It's probably polling it once here, and then it's still rendering, and it's still colliding, and we poll it again, so we see it set a second time. And then when we get over here, it's not colliding anymore, but it has this fifth sprite, which is number 7, and it just simply stays at 7 because it doesn't need to do any more work. And then we get the fifth sprite with the 7 way down here. So we do see the collision, but we're polling it all the time. So we're constantly resetting the register, and it does make a certain amount of sense that their logic might set this, and then later on it would set that with this number in there and so on, okay? And because we're polling all the while, we're going to see them at different points in time. So if we look at this and we back it up, what do we got? 16, 32, there you go. Oh, there's another one. So here is this line here where it says, I've got a fifth sprite and it's number 7, and you can sort of see it wanting to scan it. We catch it looking at number 3, and then we see it at 7. There's the collision bit again. And we go along, and it gets to the end of the line and it says, okay, there was 5 on a line and it's number 7. So there's the end of the previous line. There's 16 and 32, 31, 30. And you can again see it starting to pull here or maybe there for that line that ends with the fifth flag. And this is the end of the previous one. So there's 16, 32. And again, you see it starting to count up and so on. There's a collision. And you see it counting to the rest of the sprites all the way to the end. And we don't have a fifth on this particular line. So it gets all the way to the 32nd one. All right. So I think this kind of definitively tells us what you can expect to see if you just endlessly spin poll the VDP status register, and what's going to happen when you've got 5 on a line or a collision, and when you're going to see that information. Now, I can't explain, I can't fathom why the TI-99 chip would be counting in the fifth sprite register while it's currently rendering the line. I would have thought that it would have done the way I did it, and that is to count while it's scanning the SAT table and set the fifth sprite register at that point. But I mean, who knows? Maybe they saved a couple of transistors. There's going to be many ways to skin this cat, okay? I'm just saying. So that's what's going on in there. If you run into some articles and you see some people saying, hey, I got 64 or I've got, even more, 128 sprites on the screen at once, that's how they're doing it. Now you have to be careful, of course, that you don't try to put, all in, or rather, you don't try to put all 64 up here in the top. You can only have 32 on any given line. Period. Okay? And modulo the speed of the CPU, I mean, you can see we're polling. We can do it pretty quick, but even in the single instruction spinning internally, polling that status register, it's not going to do a perfect job. You're not going to be able to poll, identify that flag on, and update the set registers and all that stuff on a very exact and specific line. You may be late, is my point, by a line, or even more, depending on your application, by the time it gets done doing whatever it needs to do. So if you're going to use this technique, you might have 32 up here, and you might want to leave some amount of visual gap of some number of lines where you don't have to care about what sprites are there. Then you can have 32 sprites, another gap, and 32 more, and so on. And the way you identify where you are on the screen using this particular technique is you just purposely put a fifth sprite somewhere and wait until that fifth sprite flag goes on. And you can ask, which sprite it is, if you even care. You might only care about the fifth sprite flag and not the number if you're careful, and you know by the design of your program, for example, that there is never going to be 5 on a line except for that one case or however you want to do it. This is what you got to work with. Now, you can see these zeros, I mean, this is the real chip. And you can get garbage in here based on, well, what I presume is, its internal state and some timing back and forth between the CPU bus and the VDP internal logic. So back to that spin loop inside the interrupt handler, for example. When I kind of chuckled and said I wouldn't do this, I absolutely wouldn't do this. Certainly not on its own. I would, like I said, I'd probably do this while counting. That would slow the loop down and make your hesitation greater, by the way, to react to the point in time when the flag goes on. My point being that you may miss it. And in this particular case, what would it do? It would stay in here until the whole next screen is rendered. It might see it on the next frame. Honestly, I would eventually probably see it somewhere, but statistically, given the behavior that we've seen so far with the TI-99 VDP family, it's not always guaranteed to be accurate due to these clock synchronization problems. So be careful. Don't write an absolute endless loop like this. I get upset when my employees do this at any event. I always would count and say, look, if I haven't seen it within, in this case, I'm going at 10 megahertz with this CPU. In the days when you had your MSX and your other, in the retro years, nothing ran at 10 megahertz. So if you couldn't see it within 8,000 samples, you ain't going to get it, and you might want to terminate that loop early, just to make sure that your program can wake up and proceed on its merry way, especially if you're going to do this in the middle of an interrupt handler. All right, these are just recipes for seizing up a machine when something goes wrong. That's all, okay? This is beside the point, however. Clearly, you can use this kind of logic. I just am surprised that somebody would recommend putting it in an interrupt handler. That's all. Okay, so now you got it here. Okay, I'd like to hear your comments below. How would you take advantage of using this, and for what purposes, And maybe there's other applications you could use this for, other than getting more sprites on the screen. Any thoughts on that? I'd love to hear it in the comments below, or jump onto the Discord and we'll have a nice chat about it. Thanks. I'll see you later.